Our next topic today would be total internal reflection. Total internal reflection. Okay, we are studying refraction. Still, why total internal reflection came in? So we will see that. Okay. Now, in order to understand total internal reflection, so it's something that we teach in refraction itself, but why are we learning it in refraction? We will see it now. Okay. Now let's say I have an interface out here. This is my interface, and the medium down here is the denser medium. This is a denser medium, and this is my rarer medium. Is this much fine? This is my rarer medium. This is my denser medium. Okay. Now, light will be incident from the denser to the rarer. So obviously the concept of refraction holds because you're having an interface. So let me take an incident ray, and my incident ray is such that it is incident. This is my incident ray. Okay. And I'm supposed to have a normal. So let me create the normal. Right. So this is my normal. So I'm going from denser to rarer. So what do I expect? I expect that when I go from denser to rarer, my refracted ray will be bending away from the normal. Sorry, my refracted ray would bend away from the normal. Is there any issue to understand this? Obviously, there is some reflection also will take place. Some reflection will take place. I'm not bothered on that as of now. This is my refracted ray. Okay. What I do now, I start marking my angle of incidence, and this is my angle of, this is my angle of incidence, and this is my angle of refraction, where R will be greater than I. Right. In my next iteration, what I'm trying to do is that I am increasing my angle of incidence now. Let my angle of incidence be this. I've increased my angle of incidence, and let me plot my normal. So this is my normal. So what do I expect? I expect that my refracted ray will bend further away from the normal. Something like this. Tell me, is there anything difficult in understanding this part? No, right? So if I'm allowed to write this as I1, R1, and I'm taking now I2, where I2 is now greater than I1, and if I see R2 has also become greater than R1. Are we fine? Okay. Now what we do, we further keep on increasing the angle of incidence. We further keep on increasing the angle of incidence, and I find that this is almost parallel. So let me increase it further. So let's say like this, and I draw my normal. This is my normal. Now this is the beauty. I will find that my refracted ray has now disappeared, and the refracted ray has almost aligned itself with the interface. It has aligned itself with the interface. Right? If I look at my angle of refraction now, R3, this is equal to 90 degree. Fine. And on my fourth iteration, I increase the angle of incidence further beyond this. Okay, further beyond this. So and now what will I see? I will see that my angle of my refracted ray won't form at all. Look here, the refracted ray is bending away from the normal, now became aligned with the interface, means the angle of refraction is now 90 degree. If I go further, I will find that no refraction happens. No refraction happens. In fact, whatever ray is there, that ray completely comes inside. Now I won't call this as a refracted ray. This has become a refracted ray. Okay, this is known as total internal reflection. Total internal reflection. Okay, total internal reflection. Children, please be okay. Please understand one thing. Reflection, some reflection will always be there. There is always some reflection that nobody can change. But in this case, everything is complete reflection. Diagram is not exactly correct because the angle of incidence here will be equal to the angle of reflection. Okay, so it will work here. No, it won't work here. So these two angles should be same. The angle of incidence should be equal to the angle of reflection. So there is no more refracted ray. There is a complete reflection takes place. And the angle, the minimum angle at which the refracted ray makes an angle of 90 degree, or we call it the angle of refraction becomes 90 degree. That angle is known as the critical angle. This is a critical angle for 90. Critical means is a warning for you. If you now increase the angle of for any angle of incidence, what does the critical angles signify? That for any angle of incidence which is greater than IC, you will have total internal reflection. You won't get the refracted ray. Refraction as a phenomenon will not happen at all. Understood? Up to internal critical angle, you will see minor reflection and refraction happening. At critical angle, the angle of refraction will become 90 degree, and beyond the critical angle, there won't be any refracted ray at all. There won't be any refraction. Everything will be total internal reflection. So it is a phenomenon due to which a ray of light, when it is passing from denser to rarer, makes an angle of incidence greater than the critical angle for the incident medium. Greater than the critical angle for the incidence medium. In such a scenario, the refraction does not take place and the ray is completely reflected back in the same medium. So in another way to understand, look, this is medium, say this is the denser medium, this is the rarer medium. The ray is trapped back in this medium itself. You don't allow the ray to escape. Okay? Now, total internal reflection applications are seen in prism. In prism, we do total internal reflection, and another application we will study is optical fibers. Let's first see prism and then we'll see optical fibers. Okay. Let's take a isosceles prism, a prism which is say isosceles. Will I get it from here? I don't think so. Okay. You use total internal reflection to turn images by 90 degree using a prism. So this is 90, 45, and say this is also 45. This is a prism. Okay. Now let's look at the incident ray. Okay. This is my incident ray. Now I'll draw for one surface, it will become clear to you. For this surface, the incident ray is normal. The incident ray is incident normally. When you are incident normally, you just pass through, right? If you look at the other surface, let's look at the other surface, then I have this. Fine. And then it will undergo total internal reflection. So whatever angle of incidence it is making, the ray will come out with the same angle of reflection. All right, fine. And instead of coming out like this, now don't you think it is at 90 degrees, so it will just come out, right? So we can make for another pair of incident ray. And imagine you had an object like this. See, you had an object like this. Now look at the head rays. Look at the head ray. The head ray was on top. Head ray has come this side. This is the tail ray. All right. So the image that you will get is flipped by 90 degree. Did you understand? Arjun, you don't get the bars, right? If you sit a little bit this side from next time, you're comfortable? Yeah, fine. We can have some more type of combinations. Say this is 90 and 45, 45. So I have a 90 out here. I have 45 degree, 45 degree. And let me take my incident ray now. That was this. The trapezium was that. Just 1 minute. Can I see that diagram? One was 1 minute. Huh? Let's go confused. Yeah, not on this orientation. This was for the trapezoidal children. Sorry. Yeah, we'll just. Yeah. Will be on this side. Okay, 1 minute. The drawing is not correct. 1 minute. Yeah. This is 45, 45, and this is 90. So in this case, you will have an incident ray just gone this way, and then I have my normal out here. Sorry, I'll have my normal out here. Okay, that's normally. This, and then we'll have another refractive index out here, sorry, normal out here, and your ray of light will come back like this. Can you see the head arrow? Head arrow has come at the bottom. So this is called flipping the image upside down. Flipping the image upside down. And the third one we see is for trapezoidal type of prism. Okay. Here we keep the image on the same parallel, but we will just flip the image upside down. So parallel rays come this way, and this ray will come here. The ray, sorry. My drawing might be a little bit upside down, but it happens at the same parallels. So look at the head ray now. The head ray which was on top has come at bottom. So in one you flip the image by 90 degree, in one you flip the image by 180 degree, and in another one you just flipped it upside down on the same parallel. Fine. This is total internal reflection as seen for a prism. Now we need to understand about optical fibers. Shall I go ahead? Okay. So now this is where you can expect questions, theoretical questions. Optical fibers. Optical fibers have brought the revolution in communication. All the broadbands that you have in your house, okay, the internets that we are using, they all have a cable which is actually connected to your modem, and you might be thinking that that cable is carrying an electrical signal. No, it is not a cable. It is a small tube which is actually carrying a light ray. That's why it's called optical fiber. Now what happens, as the length increases for cable, the resistance increases, and so the signal drops. In optical cable, one of the good part is that you are carrying an optical signal far off distance without any loss. With no loss, you are carrying that signal from here to far off places. Okay. Now in that case, in physics we call a device, there are devices, there's a device called transducer. A transducer is something which can take a mechanical input, convert it back to electrical, take an electrical input, convert it back to electrical, take an electrical, convert it to optical. Means you want an electrical signal to travel from here to here. In between, there won't be any electrical signal. The signal will be transferred back to some mechanical disturbance, and again the mechanical disturbance will carry the signal out from here to there. Okay, it can be an optical interface in between. The optical will carry there. Again, at one end, it will be then carried back from your, like your speaker is also a sort of transducer. The speaker carries an electrical signal, finally converting back into vibrations, and you hear sound energy from it. Okay. Now, what is an optical fiber? An optical fiber is made up of materials like very fine quality glass, composite glass we call it. Not that simple. Okay. And they would look like, let's just look like strands of needles, flexible needles, composite glass or quartz fiber. And when they come out, they're just like very fine, very fine. So when these Jio and Airtel technicians come to your houses for any sort of problem, always see they'll carry one pair of scissors which they are very reluctant to give it to. Those scissors are extremely sharp, used to cut this optical fiber. So an optical fiber will have two parts. The optical fiber has a part which is known as the core, and there will be another part which will be known as the cladding. Cladding, you know, right? something that is covering the surface. Okay, so we call this as the cladding. Optical fiber is designed in such a manner that the refractive index of the core will always be more than the refractive index of the cladding. Higher the refractive index, more is the ability for a material to bend light. And since we are looking for total internal reflection, our main hunt will be bend the light as much as possible so that it cannot escape. So to bend the light, you need more refractive index. That's why the core will have a refractive index which is more than the cladding. And what happens? The core also has less absorption. So what they do is that they will make use of an optical signal, okay? An optical signal to enter this core in such a manner that the optical signal is made to enter with an angle which is more than the can you make less noise out here, please? Which is actually less than the which is more than the critical angle, okay? Which is more than the critical angle of this core material. As a result, what will happen? This ray of light will undergo total internal reflection. Nothing is able to escape. See, if you see this as a piece of energy, nothing will be escaping. Are you fine? So the intensity, say if 100%, if 100% intensity signal is given to it, over 1 kilometer, greater than 95% reception is possible. Over 1 kilometer. This is fantastic. If you give a 100% intensity signal, that is a light, and it will come out as a concentrated light. This is something like having a glass slab which is as thick as glass does not block light, right? If I illuminate a torch out here, you see the same illumination on the other side. Now this is like a glass slab which is 1 kilometer thick. And if you illuminate here, you see the same illumination on the other side. Are you getting it? So these are also used for making those tubes through which we do endoscopy. Like you want to see what is the condition of my liver, my GI tract. So when you do endoscopy, God forbid doesn't happen. So the tube always has a small light. And the tube is made to insert through your esophagus. You can literally feel it is going inside. I've undergone this. So they will check your GI tract, 2 minutes or 1.5 minutes. And they will check your upper tract, your gastrointestinal tract and all, and immediately it will come out and it will give you a very clear report. This is very common for any ENT job, ear, nose, throat, GI tract. So there also we use this. So is it clear? An optical fiber is the one which is responsible for all communication. There are hundreds of optical fibers which are laid below the ocean floor. How is the internet traveling across continents? It's all fibers. There are big cables which are below the ocean floor. We have all the internet that comes to India come at Chennai, first of all, okay? So it will be coming down at Chennai, and from there, these cables are laid across. And they do not undergo any sort of cuts or anything. There is no voltage. Even the cable which is coming and striking at your modem, which is coming through the ceiling and all, that is also an optical fiber. And if you take the cable properly and see it, you'll see a red dot light glowing. There is no voltage that comes. It's a light signal that is traveling across all apartments. And transmission quality is excellent. You can achieve very high bandwidth because the signal hardly dies down. So remember, we will have a clad material and a core material. The core is such design that there is less absorption. Always there will be some absorption. Absorption is minimized. Losses are completely eliminated and no sort of refraction is seen. So if you enter the light at an angle which is more than the critical angle, then it will continue. Diamond, for example. Diamond glitters a lot because diamond is so dense. The critical angle IC for diamond is almost 24 degrees. Means any ray of light, how much is 24 degree? Very small angle. Any ray of light which is more than 24 degrees cannot escape diamond. Have you understood? And now you give it a crystalline look. So put a ray of light on diamond. Acha, since we were talking, You know, the Taj Mahal does not have any light in it. Taj Mahal does not have any light. You can't visit the Taj Mahal at night. You can visit the Taj Mahal at night only on the full moon night. There's a special ticket. The ticket prices are very costly. And the Taj is illuminated only by the moon's light. So that's the marble. And if you go inside, then every wall of the Taj has got all these precious stones and gems put out there. And actually the beauty of the walls come out when the moonlight goes and hits it. So any ray of light which hits diamond, and inside the ray of light has created an angle of incidence more than 24, that ray will never come out. It will keep on reflecting inside diamond. So shows the wonderful brilliance of diamond is seen due to that. This is fine. Okay. You can also do, there is an experiment in your book. You can also do that. You can take a glass and take a glass of milk. Milk is what? Milk is a colloid. Okay, you take a glass of milk and fill it with milk and take laser beams. Laser beams are, because laser beams are monochromatic, single ray. They do not undergo any deviation. There is no scattering. So what do? You actually try to illuminate a laser beam from here. So the laser beam will initially go here and then undergo refraction. It will enter. Then you will find that the laser beam has actually escaped and you will see the dot on your ceiling. Right? Increase this, your torch, the laser torch which you're holding like this, increase its angle of incidence. Then, if you increase its angle of incidence, then you will find that it has gone inside now. Now it is no more able to, and you will see the illumination right at the bottom. Total internal reflection has happened. Instead of going up, you come down. You can do that for side, you can do this from bottom, possible. In which the beam is not seen on the opposite side. The beam will be seen on your side itself. Fine. So far? So this now brings us to refraction through spherical surfaces, in which we will get into lenses and all. Spherical surfaces. Now, when you talk about spherical surfaces, transparent spherical surface. So in transparent spherical surface, now this is not a mirror, this is a transparent spherical surface. Sir, are you talking about a lens? Well, no, I'm not talking about a lens also. It's just a spherical surface. Instead of a plain glass slab, it's curved. So the laws of refraction hold here also. Angle of, what was the laws of refraction? The refracted ray, the incident ray, and the normal at the point where refraction happens, they are lie on the same plane. But the only thing we will say, everything that the angle it makes with the tangent to this plane, okay, because it is curved now. Are you understanding? You have to make a tangent out here, and then the normal made with the tangent to this curved surface. The curved surface are taken so big, the curved surface curvatures are so big that every small portion of the curve is almost taken to be as linear, which is plane or straight surface. Is this thing understood? And while we actually study our aperture, what is aperture? The amount of surface that you are actually exposing to the incident beam. Suppose this is the incident beam. This aperture is made small, as a result of which this distance, children, this is, say, AB. AB is no more an arc. AB will be considered to be as a straight line. This is the consideration with which we'll go. So first, what we will see the formula for refraction at a spherical surface. We'll see the derivation for this refraction at a spherical surface. Then you might ask, sir, what is a lens? A lens is a combination of two spherical surfaces in which one surface is sufficiently curved. Inner surface can be curved or the outer surface can be curved, and their thickness is very, very thin. In a lens, the thickness is very thin, but it will be combination of two spherical surfaces. Right now, what we are going to study is refraction through one spherical surface. Okay, are we fine? So we'll use this diagram itself. So this spherical surface is a part of a sphere, So obviously I should have something which is known as the center of curvature of this spherical surface. Are we fine? Okay. And we take any arbitrary point, which is my object O, right? And from O, let's say I have, as a children, is this thing clear? Because unnecessarily the diagram will get, yeah, I'm just making a fresh diagram because I feel on this one, what will happen? It will get jumbled up. Okay. So this is my spherical surface and I have to have a center of curvature, which is C, and I have a point where the object is. Now, radius at the point of contact is always normal. Right? Let this point be point N. This is the radius from the center of curvature, and I take an incident ray. My incident ray from the object, hits at N. So this is my incident ray and forms an image out here. Okay, I call this as my image point, and right, the refractive index of this medium is N1 and of this medium is N2. Children, try to understand one thing. One minute, eyes on the board, please. This is not a mirror. This is a lens. Not a lens, spherical surface. Everything on this side is a part of the spherical surface. This is not air. This side is air. Or in other words, to be very generic, this is N1 medium. Everything on this side is N2 medium. That's why in your book, this portion will be shaded. I'm not shading it because it will make it look clumsy, right? This part is N2 medium. Remember, if you remember this, then your all calculations will come correct. N1 medium in which light is incident from, and N2 is refractive index of medium where light has entered. From where it comes, or not it, from where ray comes, and this is in crude language, where the ray travels to. Now we find ray is now coming from the air, which is with refractive index N1, and now it has gone inside the spherical surface, which is refractive index N2. Okay, so this, and what we do, we can take one point B out here, and our consideration is that in a sense I can say, so this is M, so NB is equal to NM. Fine? Okay. Then it's very easy derivation. Don't even, obviously you will need some object distance in everything. Okay. So first mark what is your object distance. From here to here is your object distance. This is your radius of curvature. Fine. And if I extend it further, from this to this would be your image distance. Shall we then mark them? Okay, so let's mark them with this color itself, this, and this say this. This is U, this is R, and this is V. Any doubts so far? Not at all. Your eyes should be on three angles. Okay, this angle, and this angle. These three angles your eyes should be on. Are we fine? Okay. This is my angle of incidence, right? And this will become my angle of refraction. Are we okay? So your eyes should be on three angles: angle 1, angle 2, angle 3. And just remember these three things. How to get this derivation? The points to how to remember this derivation is U, R, and V. You should try to find out in the diagram. Then try to find out 1, 2, and 3 angles. These three you should find out. And the third one should be, if you look at I as an angle, it is an exterior angle for 1 plus 2. Look, I is an exterior angle for 1 plus 2, and 2 is an exterior angle for R plus 3. 2 is an exterior angle for R plus 3, which means R is equal to 3 minus 2. Sorry, 2 minus 3. R is equal to 2 minus 3. Children, just absorb this thing. Have you understood? Draw the diagram. After you draw the diagram, there is nothing to memorize. Spot for 1, 2, 3. Then also spot for that. Once you have found this, this, and this one will form an exterior angle. This one will form an exterior angle for these two. Okay. So let's see the derivation and try to get the reflection formula for a spherical surface. I'm making the whole thing small now a bit. Oh. It doesn't allow. Yeah. I'm only making it for this. Chalo bacha. Let's start. Tan of 1. Can you tell me what is tan 1 equal to? Tan 1 is Mn by OB. Mn by OM. Do you agree? That we will say later on. This is tan. Fine. What is tan 2? Tan 2 is Mn by MC. What is tan 3? Mn by Mi. So you've got your thing. You have an object distance, you have the R, and you have the image distance. See, it becomes very easy now. Okay. Now, when 1, 2, and 3 angles are very small, then tan 1 is equal to 1, tan 2 is equal to 2, and tan 3 is equal to 3. Are we fine? Okay, very good. So if I now look at I is an exterior angle for 1 plus 2. Agreed, children? Therefore, I is equal to how much? What is 1? 1 is Mn. 1 is Mn divided by OM. OM can be now written as OB plus Mn by tan 2, that is MC, which can be written as BC, right? Because B and M are very, very close. We can write this. And similarly, r can be written as 2 is equal to 3 plus r. So r can be written as 2 minus 3. R can be written as 2 minus 3. Take. So what is 2? Mn by Bc minus 3. 3 is Mn by Mi. I am writing it as Bi. B and M are very close. This much is okay? Can I go ahead? Okay. So I'm going ahead. Then look, this formula we will see. N1 sine 1 sine I is equal to N2 sine R, and this is Snell's law. Do not get worried, we will just see this. Always remember I and 1 looked similar, so N1 sine 1. Just let's see this. What is Snell's law? Tell me. Sine I by sine R is equal to eta 2 with respect to 1, right? 1 is from where the light is coming. Eta 2 with respect to 1 in my language I can write as this manner. No issues. This I can further write is eta 1 with respect to air into eta 2 with respect to air with respect to 1. This, so this is, remember, this is sine I divided by sine R. Now, what is this? Eta 2. This can be written as 1 upon, I can write as 1 upon eta 1 with respect to A. So my sine I by sine R becomes equals to what? 1 upon eta 1 into eta 2. So if I cross multiply now, I get eta 1 sine I is equal to eta 2 sine R. This is what I have used. No, and it's not required to show. I'm saying if you get fumbled up on this one, the way to remember is this. Fine. Now, for small angles, sine I is equal to I, sine R is equal to R. So eta 1 I should be equal to eta 2 R. Agreed? So eta 1 into I. So let's look back. What was I? What was the value of I? Mn, will take Mn combined, and it is 1 by OB plus 1 by BC. 1 by OB, so we will take eta 1 Mn common, 1 by OB plus 1 by BC should be equal to, similarly here also Mn can come common by eta 1, sorry children, there's one. This is eta 1 Mn is same as, we write here eta 2 Mn. Okay, and let's see here, it was BC minus BI, 1 upon BC minus 1 upon BI. Fine. Mn can take away Mn. Okay, so what do we have? We have eta 1 upon OB, right? And eta 1 upon OB plus eta 1 upon BC is equal to eta 2 upon BC minus eta 2 upon BI. Okay, this means I can write eta 2 minus eta 1 by BC, and this side what will I write? N1 by OB plus N2 by BI. Now we will put our sign convention. Now put the sign convention. Acha, sign convention, the best way to remember when you get into grade 12 is that you always measure opposite to the incident ray. You always measure anything opposite to the incident ray, right? So OB, you remember O and B. B is this side and O was this side. So this becomes eta 1 by negative U, right? And BI, B was here and I was on this side. So this is N2 by V is equal to N2 minus N1 upon R. So your final formula says N2, always V is important. So it comes first. N1 by U is equal to N2 minus N1 upon R. This is the formula for reflection at a spherical surface. What you need to remember, don't remember it as, remember this formula. You will confuse up in the next derivation when we do lens formula. Everyone confuses. The reason is this is a parent formula. This is always true. But while this is true, you should remember N2 is the medium in which the ray went inside. N1 is the medium from where the ray came. This thing keep in mind. This is known as refraction at a spherical surface. Now we will see the lens formula. So you have a lens formula which is known as the lens maker's formula, and then you have one which is known as the thin lens formula. Thin lens formula is what you have learned in grade 10. 1 by F is equal to 1 by V minus 1 by U. This is N2. Fine. You will be able to derive now 3 angles. Then find the value of I and R. Then put this. Then just do some. At last you hand over the signs. I don't know whether we'll be able to do, but we'll still try. We should be able to do. Okay. Let's see the next one. Our next one is the lens maker's formula. Or the lens formula. Okay. So here we'll have an object. This is O and this is I, right? This is your incident ray, reflected ray, and obviously this much of a distance is your, sorry, this is your object distance roughly, okay, and this is very, very thin lens, and this is your image distance. This is your object distance U, image distance. This is very thin, very thin. I mean, there's no difference between this area and this area. Now, how to understand this particular image formation? We will break this up into 2 cases. The first case would be the first spherical surface, okay? Remember, children, this is eta 1, this is eta 1, everything inside is eta 2 now. So we'll break this. So this image formation actually happens in this way. First, we were considering only AB, this part. Fine. And obviously, I will have some what you call center of curvature of this. See, this is like, this is a spherical surface, will have a center of curvature on this side. This is another spherical surface which will have, if this is say C1, it will have another C2 on this side. This is the idea. Okay, so I have a C1 on this side, right? and I have my incident ray. My incident ray goes from here, and diagram still remains the same as it was previously. The first diagram is not that difficult to understand, and this is my reflector. So let's put something. Let this be the object, this be the image, okay, and let this be N. Rest you know. Now I'm taking this as I1. Try to imagine what happens. This diagram is first broken into first part where there is a refraction and you get an image I1. I1 image will now serve as object for this particular side. So twice we will apply the refraction through a spherical surface formula. We'll apply twice. Once for this side and once for the other side. Are we fine? So I can call this as this distance. I can say that this is U, this distance is V, and I'll call this as V1 now. Okay, V1 for I1, and this is R1. Fine. So let's recall our formula. Our formula was eta 2 by V minus eta 1 by U is equal to eta 2 minus eta 1 upon R. Try to put this formula. Instead of V, which is the image distance, it becomes V dash, or I use the word V1. V1. Eta 2. Eta 2 is that medium in which the light entered. In which the light entered. In which the light entered. No change. And eta 1 is that medium from where light came, is equal to eta 2 minus eta 1 upon R1. No doubt, children? Absolutely okay? Okay. If you try to draw the other image, it will be something like this, that now the other side. Now see children, everything this side is eta 2, everything this side is eta 1. Okay? And you have your what do you call I dash, and your final image is here, right? Your incident ray now actually is coming from inside, okay, and it is bending away from the normal, right? Okay. And what are the measurements that you have? You will have a, this is not that important, this to decode this diagram, but this is your final image. This is my final image, which is I, right? Now what is your object? I1 is your object. Got it? I1 is your object. And what is your object distance? Your object distance is, now your object distance will be measured from here to I1. Right. I am taking this surface as X and I'm taking this surface as Y. So this was X and this is Y. Is this much understood? Okay. Now let's apply this formula once again. Okay. Now we have by V. V is what? Image. What is your image now out here? Your image out here, sorry, this much portion is your V, the final one. And this is something that you have to appreciate. Now you will say this is yi1, but I would say, children, yi1 is also equal to v dash only, v1 only, because x and y are very close to each other. Length is thin, so x is close, very close to y, means x almost coincides with y. Did you understand, children? Right? So yi1, just look once, yi1 can be considered as v1 and this guy is v. Okay, so now try to put the formula once again. Children, v is what? Image distance. In this case, what is the image distance? V, right? N2 is where the light entered. So this here will be N1, the light entered N1, right? Then we have the object distance. The object distance is V1. And N1 is from where light came. Light came from N2, right? And on this side, now if this is R1, I would call this distance, I would call this distance as R2. Are we fine? R2. Again, N2, eta 2. Eta 2 means where light entered. Eta 1. Where light came from. Eta 2. Perfect. Can I add these two? If I add these two, then this one cancels this one. Fine. This one cancels this one. It becomes eta 1 common 1 upon v minus 1 upon u. Just see, eta 1 common 1 upon v minus 1 upon u. Arjun, okay? Now what I am doing here, I am taking eta 2 minus eta 1 common. If I take eta 2 minus eta 1 common, then here I get a minus sign out. This is eta 2 minus eta 1, this is eta 1 minus eta 2. This can also be written as negative of eta 2 minus eta 1 upon R2. Fine. So this becomes 1 upon R2 minus 1 upon, oh, I'm adding. So 1 upon R1 minus 1 upon R2. Sorry. 1 upon R1 minus 1 upon R2. Are we fine? Now divide eta 1 on both sides. So what do you get? 1 by v minus 1 upon u is equal to eta 2 by eta 1 minus 1 by R1 minus 1 by R2. 1 by R1 minus 1 by R2. Correct. Yeah. Clear? Anywhere Arjun doubt, just ask me. What is eta 2 by eta 1? What is eta 2 by eta 1? Let's just see. Eta 2 by eta 1. This is equal to eta 2 into 1 by eta 1. Right? How can you write this? Eta 2 can be written as 2 with respect to air into 1 by eta 1 with respect to air. This can be written as this into eta air with respect to 1. This is same as eta 2 with respect to 1, eta 2, 1. Yeah. Right, eta 2 by eta 1 is eta 2. So I go back to my slide and I write this formula as 1 upon v minus 1 upon u is equal to eta 2 1 minus 1 by R1 minus R2. Children, this is my lens formula or lens maker's formula, right? Now just give one common thought. I'm just changing the color. Give one common thought. If object is at infinity, then what happens to this quantity 1 upon u becomes 0. And when object is at infinity, image is formed at focus. So this becomes this particular expression becomes 1 upon f is equal to eta 2 1 minus 1 1 by r2 minus 1 by r1 1 by r1 minus 1 by r2. Did you understand this or not? If the object is at infinity, the image is formed at focus. So V becomes F, U 1 by infinity is 0. And if you look at these two equations, children, if you look at these two equations, then RHS is same. Therefore, LHS must be same, which is 1 by V minus 1 by U is 1 upon F. This is your thin lens formula. Both derived together. Everything comes from the refraction at a spherical surface, and there keep one thing in mind: eta 2 is where light entered, eta 1 is where light came from. Not for this formula, for the previous one, because this is the mother formula that we will be applying. If you understand this formula, your derivation will become very easy. So this is the mother formula. From this mother formula, we will be able to find this criteria, the first equation, the second equation, add both the equations, then we get this. Then after that, we have one more thing, which is eta 2 by eta 1. You should also know what is eta 2 by eta 1 is nothing but 2 with respect to 1. Then you find left hand side is, then you use this criteria and you replace this quantity by 1 upon f, and using those you get. So first formula that you learned was what? The first formula that I learned was the formula for refraction at a spherical surface. What was the next one that you learned? That is this one. What is this? This is the lens maker's formula. What is this? This is the thin lens formula. In our next class, we will be doing a couple of problems first before going ahead with prism and other things. Okay, I think after this it will come for prism, but at this level we will have to do some formulas. So you now know the mirror formula, you now know the lens formula, and then here we will see some criteria for image formation, which you all know. Anyways, we'll derive those, or we'll not derive those, we will study those. Then we will see power as combination of lenses, and then we'll spend one class at least in numericals. After that, we will get into prism, and once you get into prism, then it's all about optical instrument, which is your microscope. Till this much, have you understood? Right.